Welcome to video 8.2 in our first Principles of Astrophotography series. In this video we discuss the angular separation between two stars at which you can tell that there are two stars instead of one.
The separation depends on the telescope aperture, with larger apertures giving better resolution. This is a theme.
Yeah, this might not be the last time we say it either. This video is based on section 8.2 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility.
What I'm showing here are two Airy patterns on the right that are separated by twice the disk radius. So in the previous video we talked about the distance between the center of an Airy pattern. Airy patterns are created by pinpoint stars passing through the optics and then created on the sensor. You get these patterns. So the disk radius, this is considered to be the disk, the Airy disk, and there's a maximum intensity here and a zero intensity there, and that distance, angular distance between the two, is called the disk radius, Airy disk radius. So from here to here is the disk radius. Also from here to here is the disk radius. So this total distance between those two Airy patterns, between the centers of those patterns, is twice the Airy disk radius. And if I asked Ren whether you can tell that there are two stars there rather than one.
Can I poll the audience?
Sure.
Yes, there are two.
Okay.
Thanks, guys.
People, good job. So here's this exact same pattern, but graphically on the left side. Here's the center of the peak of the right star. Here's the center of the peak of the left star. And both of the Airy disk radii coincide, so both of these reach a minimum right there. So this guy comes down and reaches a minimum. This guy comes down and reaches a minimum. The minima coincide, and you get this nice dark spot, which makes it easy to tell these apart. So one way to think about this, and we talk about this in the book, is you've got a car approaching from a distance, and when it's really, really far away, the two headlights, being so far away, look like they're merged into one. Then as you get closer and closer, you begin to think, okay, maybe this is a car, not a motorcycle. And then once it gets really close and you say, oh yeah, I can tell that's a car for sure, because I can definitely see both headlights. So we're doing that process in reverse. We're starting with the car up close to you and then backing away from you. Okay, so the Rayleigh limit.
Principle 110. The Rayleigh limit holds that two stars can just be resolved if their angular separation equals the Airy disk radius.
Perfect. So here we had an angular separation of the two stars of twice the Airy disk radius. The Rayleigh criterion holds that if you put them at the Airy disk radius apart. So here's the center of the right star, the center of the left star. This black edge of the Airy disk of the left star coincides with the peak of the right star, and the edge of the Airy disk of the right star coincides with the peak of the left star. So you can see that here. Here's the right star peak, the left star peak. The right star comes down and reaches its minimum at the same place that the left star has its maximums. And then vice versa for the left and the right stars. So this is what Lord Rayleigh came up with. He was a dairy farmer, I understand it. He came up with this criterion between feeding his chickens or something.
Wow.
So, yeah.
Smart farmer.
Smart farmer. But So I might now poll the audience and say, can you tell that there are 2 stars instead of 1 for this separation?
I think with those little bumps between them, the little black dots, I think you can tell.
So in other words, you're saying these give you a clue, the little black dots? Mm-hmm. Yeah, I think they do.
The full width to half max limit holds that 2 stars can just be resolved if their angular separation equals the full width at half maximum of the Airy profile.
So let's recall that that theta naught, the Airy disk radius, is 1.22 lambda over d. So that's the Airy disk radius, and this is the full width and half max. Which one's bigger? Well, the Airy disk radius is slightly bigger than the full width and half max, because this is 1.22 and this is 1.029. In fact, if you divide the one by the other, you'll find that the full width at half max is about 84% of the disk radius. So the full width at half max, if you separate 2 stars by that same amount, they're going to be separated by less, a shorter distance. And that's what it looks like here. So this is the full 2 stars separated by the full width at half max of a single star. And can you tell them apart? Well, that little dark spot here has gotten a little bit weaker. It was more of a divot before, and now it's getting a little bit more sketchy. But I think most people would say if you had a nice clear image like that, you could say, yeah, there's probably 2 stars instead of having one oblong star. So then finally, and this is what the car really, really far away, at this point, if you're at half the disk radius, you're pretty much out of luck in trying to distinguish those 2 stars. That gets to be the point where, yeah, you can say, well, maybe it's a little bit oblong, but when you're looking through a telescope or you're taking images, that image is dancing around anyway, and so this is probably you can't tell that there's 2 stars.
Yeah. Principle 112, resolution and aperture. We told you it'd come back. The larger the aperture, the smaller the Airy disk, and the better the resolution.
For a small aperture D, you're going to get a big Airy disk. And for a large aperture D, you're going to get a small Airy disk.
Or more pinpoint. Yeah.
Or more pinpoint stars. The smaller the disk, the better your resolution is going to be. And so that's the dependence on D. There's also a dependence on the wavelength, which says that for red light, you're going to get, like we talked about in the last video,
larger Airy disk. Yeah.
Yeah.
Dawes limit 113. This Dawes limit represents the minimum resolvable angular separation between 2 stars for visual observations and is statistically indistinguishable from the full width half max limit.
So who's Dawes and why should I care about him? He was not a dairy farmer as far as I know. He was a visual observer, and he published a paper claiming that he could distinguish 2 stars of comparable brightness at the what we now call the Dawes limit. And here it is. So he didn't publish the wavelength dependence of his criterion. He just said he published the aperture dependence of his limit. So what we've done here, in order to compare the Dawes limit with the Rayleigh limit and the full width at half max limit, is we've just said, since Dawes didn't worry about the dependence on the wavelength, we've just evaluated the Rayleigh limit and the full width at half max limit at the average visible wavelength. And what's that? Well, for red light, it's 700 nanometer wavelengths. And for violet, it's 400 nanometers. So the difference between 700 and 400 is 300, obviously. So right in between these is the average visible wavelength, which is 550 nanometers. And you can double check that by adding 150 to 400, which gives you 550, adding 150 to 550 to get 700. So if you evaluate those equations that we had before for the Rayleigh and the full width at half max, you get these. And we go through this in detail in the book. The full width is 117 divided by D, where D is measured in millimeters. The Dawes limit, he put it in for a diameter of a telescope diameter in inches. If you just convert that to millimeters, which is what we usually use today, then you get 116 divided by the diameter measured in millimeters. So I might ask, how close is this to this? And
I might say it's virtually indistinguishable.
yeah, statistically indistinguishable.
Oh, statistically.
They're virtually, yeah, they're pretty darn close to each other. And so what you'll find, and the reason why this is applicable and why it's important in astrophotography, even though it's a little bit detailed here, is that the Dawes limit is considered the very best you can possibly hope to do with your telescope. Generally, you won't even come close, as we show in a later video. You just won't come close because of atmospheric turbulence. But, as we talk about in a future video, if you're doing lucky imaging, you can actually get this kind of resolution on your telescope. What's lucky imaging? Instead of taking a picture over a 3-minute exposure or 5-minute exposure, you take 75 photos per second of Jupiter or something that's really bright, and then you freeze the seeing with these short exposures. And yeah, so this is taken right off of, I plugged this aperture of our Celestron Edge HD 9.25 into these equations up here, and I got these results for the Rayleigh and Dawes limits. And clearly the Dawes limit is stricter than the Rayleigh limit, but the Rayleigh limit is also used a lot. But I think I took it off the Gina Astro website, these values, and that's how to get them if you want to get them yourself.
Yeah, and this is actually really important too in astrophotography. Nothing is clean and dry in the sky. You're never going to have you'll sometimes have two stars of similar magnitude right next to each other, but you're going to have a brighter star and a dimmer star. And when we get into processing, we're using things like Blur Exterminator to help us to determine those two stars.
These rings, diffraction rings here, are very difficult to see visually unless the conditions are absolutely perfect, and even more difficult to photograph. But in the book we reference one, I think it was on cloudy nights, a fellow posted his images of a star that showed diffraction rings. I was pretty impressed at an actual image that he took. So well, thank you so much for watching,
and we'll see you next time.